Hi, this is Gabriel, and my goal today is to offer a $35 video for free for a limited time. If you like what you see and you meet someone that can get a lot of value out of this, let them know about this video. So you're going to want to remember this website, mastermathcourses.com. Remember to watch the video from beginning to end so that you're able to get all the mindsets for this particular problem from this walkthrough.
Hi, it's Gabriel, and I'm here to walk through another problem. Today we're going to be covering Rolle's theorem, and our function is f of x is equal to 3x cubed minus 2x squared minus 8x plus 3. And Rolle's theorem has an interval for which we want to work on, which in our case would be 0 to 2. And the question says, does the function satisfy Rolle's theorem? If so, find the value c. So, well, there's three rules that it needs to satisfy. One is f has to be continuous on a closed interval between a and b. F has to be differentiable between an open interval a comma b. And 3, f of a has to equal f of b. Well, first, one of the first things that I wanted to cover here was the idea of a function. A function, remember, has to pass the vertical line test. In our case, our function will look something like this. So this is the y-axis. This is the x-axis. And it would look something like this. Kind of like a little S-shaped curve. And it would pass the vertical line test. The vertical line test says that if I draw a line from top to bottom, I must cross if it's a function, I must cross the line at just one time. An example of something that wouldn't be a function would be maybe a graph that would look like that. If I do the vertical line test now, I'm passing 2 points. So that would fail the vertical line test. So I just wanted to let you know what a function was. That's what I wanted to start off with. Now, how do we know whether f is continuous on a closed interval? Well, as it turns out, we can find the continuity is related closely with the domain of a particular function. So over here, I have names of functions. I have a polynomial function that would look something like the one we have right here. Or another example would be x squared. That would be polynomial. So would x to the 5th, and so on. A trigonometric function will look like this, like sine of x, or cosine of x, or tangent of x, all those. An exponential equation will look like this, e to the x. A rational equation is something like 1 over x. A root function would be something that looks like this. An inverse trig function are those arcsines, arc sine of x, or this one right here. A logarithmic equation would be something like log of x or ln of x. Well, if we could find the domain of these functions, then we just have to test whether the domain is within that range, and we prove that it's continuous. To find the domain of something that looks like this is pretty simple, because we learned that when this is polynomial, that the domain is all real numbers. And in fact, we also know that there's a theorem that says that f of x is always continuous from negative infinity to positive infinity. And when professors are talking about continuity, or whether a function is continuous or not, they like to think about it in terms of, well, what is discontinuous? Well, we'll say that a function is discontinuous if one of these three things happens. One, there's a vertical asymptote, right? So VA. So this type of function would have a vertical asymptote, and that's just an invisible line where the function cannot cross. Another case where the function will not be continuous is if there is a gap. In other words, the function starts off here, then it ends, and then it starts over here. That would be discontinuous. Another discontinuity that could happen is you have a hole. In other words, you have the line, then there's a hole here, and it may or may not have some point up here or down here somewhere. That would also be discontinuous. So those are kind of like the things that you want to think about. But for this particular problem, it's going to be all real numbers because there's never, if you could imagine the graph, there's never a hole, a gap, or a vertical asymptote in this case. So we know that it passes the property 1. Now, for the second property, it also has to be differentiable. What does that mean? Well, what that means is that if I take the derivative of this, can I plug in a point, any point between A and B? That's what that means. So if I take the derivative of this, I would get f prime of x is equal to, 3 times 3 is 9, not 6. 9x squared minus 4x minus 8. That's the derivative. Now, if I wanted to know whether it's differentiable, what that means is, can I plug in any number here between A and B and get a result? Well, it's almost like asking, what's the domain of the derivative instead of the original equation? Well, since this is a polynomial equation, we know that the domain always exists, right? So it doesn't matter what A and B is, even if it's 0, 2. It's going to work out. In other words, if I plug in 0 here, that should give me a result. If I plug in 2 here, that should give me a result. There isn't going to be anything within the operations that are in here that are going to give me something that's undefined or that I can't resolve. We only get undefined when we have something like this, like a rational equation. I can't divide by 0, so the operation division doesn't allow me to divide by 0. So these functions, the top 3 functions, polynomial, trigonometric, and exponential functions, have a domain that goes from negative infinity to positive infinity. So, and rational equations, well, if you remember, we can't divide by 0, so most of the time the domain is restricted for rational equations. It's also restricted with radical equations because I can't plug in a negative number into a radical. And for inverse trig functions, the only way we can get an inverse trigonometric function from something that is continuing forever and cyclical is to restrict the domain. So we restrict the domain for inverse trig functions. And for logarithmic functions, we can't plug in a negative number into a logarithmic equation because it doesn't work out. So the moral of the story is, if you have any of these equations, you're going to have a restricted domain, so we have to be a little bit more careful as to deciding whether the function is continuous or if it's differentiable. So far, though, our function has passed the first 2 tests. Now let's see if it passes the third step. Each problem presents different obstacles, and what I'm able to do with these walkthroughs is offer many similar problems to resolve wherever you're stuck.
If you're done watching this video, it's safe to assume that you found this video valuable. So refer us to your friends. And of course, we're always trying to improve, so let us know how we can do that in the comment section below.